Hello students, welcome back. Let us resume our discussion in section 7. We just went through the standard case for linear Diophantine equation. This one right here. We begin with linear Diophantine equation of this form, ax plus by equal to c. And if a and b are relatively prime, then we don't really have to worry about that GCD dividing this constant because 1 divides everything. So it has infinitely many solutions, but not only that, all those infinitely many solutions are precisely this one. Here, x0 and y0 can be found through the linear, the Euclidean algorithm. Yes, this is Bezout's linear combination expression because 1 is the GCD. So you can find x0 and y0 through Euclidean algorithm, as we went through a couple of times in section 6. And then based upon those, we get the general solution like this. That was the standard case. Now, what if we have the GCD is non-trivial? Not relatively prime, therefore we have GCD greater than 1. In that case, we can consider two cases. If D does not divide C, then there's no solution. If D divides C, then we have infinite many integer solutions. And we have precisely the same form as the standard case. Because if we divide everything by D, then you're going to get a new coefficient, A over D, and then B over D, and finally constant term C over D. So put everything into this, except for some change of characters, then you're going to get this. So the latter half of this theorem is not really worthy of our time. Let's consider the first half. If D does not divide C, then there is no solution. Well, let's prove that. We prove the contrapositive. Suppose that there is an integer solution. Then we're going to prove that D divides C. Okay? So initial step is a bit hard. Thinking about the proof by contradiction, that may be a bit difficult, but from this point on, it's going to be easy. So suppose that solution exists, so that we have ax plus by equal to c. And then we'll have to prove that D divides C. How do you do that? Well, this is a linear combination. So all linear combination is divisible by common divisors. X is divisible by D, so D times something. Y is divisible by D, so D times something. So D is common, I can factor out. So A is some alpha times D, B is some alpha times beta times D. Put those in, I'm going to get A is alpha D, B is beta D, factor D out. What do you have? We have D times some integer. So D divides C as desired. Easy, isn't it? So any common divisor divides C. GCD is also a common divisor, so it divides C. Because the contrapositive is true, the original statement is true as well. If D does not divide C, then there is no solution. When D does divide C, then we can reduce it into the standard case by dividing everything by D, so we can use the proof that we went through in the standard case. So this completes Brahmagupta's theorem on linear Diophantine equation of this form. Two unknowns, ax plus by equal to c. Now what if you have more than two unknown variables? a1x1 plus a2x2 plus and so on. In this case, things are a bit more complicated. it turns out if D does not divide C, then there's no solution. If D does divide C, then this Diophantine equation has infinite many integer solutions. Now, what is the form? Now, that's a bit different. I don't think there is general formula, unless we have some very special case. So let's just leave it at that. Our textbook out there does not bother going through the general solution either. So let's leave it at that. Line 1, as usual, as before, let's use the contrapositive. Assume the solution exists so that a1x1 plus a2x2 plus and so on exist. Then each coefficient a is divisible by d, so this is d times something. The next one is d times something. That too is d times something, and replace those by d times alpha 1, d times alpha 2, in the end d times alpha n. Factor d out, we have d times an integer. So basically the same as before, except that we had more than 2 terms. Each coefficient is divisible by d, so we have that. So that's done. If d does not divide a constant term, then there's no integer solution. Now what if d does divide? In that case, we can use an induction on n. So assume it is true for n minus 1 integers, and then we can bring it down to, let's see, okay, we start from here, this form. I think it's better to rewrite one more. Oops. Okay, and then n minus 1, xn minus 1, and 1 further still. N minus 2, xn minus 2. Okay, all right, let's write it like that. And then there are total n terms here. What we're going to do is to combine the last 2 terms. You see, this is a linear combination. Let me highlight in red. This is a linear combination of xn minus 1 and xn. So this thing is divisible by the GCD of xn minus an minus 1 and an. So common divisor divides this and also that. So this entire linear combination is that GCD times some integer, so that we can rewrite it like this as I highlighted in red. Make sense? There used to be n terms, but last 2 terms can be combined into a single term. Now what do we have? We have n minus 1 terms, n minus 2 terms here, and 1 more. So we can apply the inductive hypothesis. There are infinite many solutions for x1, x2, x3, and so on, and finally y. And then for this, the second solution, this one here equals to this. We have another base case, that 2 variables, xn minus 1 and xn, and then whatever, GCD of those, okay, that's definite. And then consequently, GCD of these is this factor here, so the GCD divides this constant term. And this constant term is basically nu c. Yeah. Shall I write c prime or something? And c prime is divisible by the GCD of an minus 1 and an, because you see GCD times the integer is C prime. So we can find a solution here by the base case. So inductive hypothesis and the base case. So we have all the solution, x1 through x minus n, and then y. But once you put y here, then we have another solution. We have another linear Diophantine equation. So we can find Sn minus 1 and Xn as well. Okay, all right. All this divisibility. And the given y, we have the second equation, which I just highlighted in red. Consequently, we have all those solutions. Okay, that proves the general case for linear Diophantine equations as well, even when we have more than 2 unknown variables. As for exercise problems, I intend to write several of those in the homework problem set, so please go ahead and work on those. As for class time, well, we already spent quite a bit of class time going through these. So that'll be sufficient. If you need more, go ahead and do some exercise problems. Some are required, some are just recommended, but there will be many. All right, that concludes lesson 3 of all those. So that concludes chapter 2 of our textbook, Divisibility Theory. And next week, we are going to begin prime number theory.